let's see, I'm not going to talk so much today about how we train our models, nor how the thresholding works. I know those are a couple of other hot topics, but this is specifically going to be about how we use the statistics to make decisions about how well the model is going to perform on future records. So the question is, how do we evaluate the performance of a model? Obviously, we have a set of statistics that we care about, and seeing higher numbers is better. Period. That's kind of like the caveman interpretation. That can work, but it will also be unsatisfying if the numbers aren't high or are on the border of feeling high. Also, high is an arbitrary definition. So how do we come up with some meaningful threshold for ourselves that we think, okay, these numbers are acceptable to me. 0.85 precision is okay. We need to actually understand what these statistics represent. Okay, so to jump into a little bit of machine learning terminology, we have features and we have labels. In our problem of screening models, features are basically things like the abstract, the publication date of records, and labels are include or exclude decisions. So the game we're playing with the screening model is predicting labels from our abstract, publication date, etc. Features. So to build a model, obviously, we need labels. We need those include, exclude decisions. To evaluate how a model is doing, in other words, to say, is the model acting correctly, we also need labels. The annoying part of this is that we want to predict how the model is going to perform on unlabeled records. In other words, we can't actually evaluate how the model is doing on those unlabeled records because we don't have any labels. So it's kind of this difficult problem to solve. And one technique that we come up with is to say, okay, well, we have to have labels to evaluate, so let's just focus only on records or on training examples that are labeled. So in our problem, that means labels being screening decisions. That means we're going to focus on records that were only screened, and we're going to do something called cross-validation. In brief, and I'm going to touch on an example of this in one slide here, but in brief, cross-validation is the idea that you take your screened records and you break them up into test and training sets. So here's a kind of a visual representation of this, and we'll jump to the next slide where we have some numbers on explicitly how this might work. So in cross-validation, let's say you have a nest with 1,000 records, and 200 of those have been screened. So kind of represented by this little matrix of examples. So about a fifth of them have been screened. So we're going to create 4 folds as part of our cross-validation. The way that the folds are set up, 50 records are going to be in the test set, and 150 are going to be in the training set. The model is trained on the training set, obviously, and the test set is held out and used for evaluating how well the model will do. So to kind of visually represent this, one fold right here, you can see that a quarter, 50, of our records are put in the test set, and 150, so 3/4, are put into the training set. We're then going to evaluate the model without giving it the labels. So critically, we will only give the features of the test set to the model that we trained over here, and then we're going to score or evaluate how well the model did in the test set. And we're going to repeat this process across all 4 of our folds, and then average up the scores that we got. And that's going to give us some idea of how well we would expect our model to generalize to other new unscreened records. So in other words, the game we're playing here is we're kind of pretending like some of our labeled records are actually unlabeled, and then using that to predict how we will generalize to future records. So there's one kind of big detail here that I hand waved, which is how do we actually score these test sets? Again, we have a model which makes include and exclude predictions, and we have labels from users of include or exclude decisions. Does anyone want to just throw out some ideas of how you might actually score that? So again, we have model says include or exclude, and we have a human, like our label, saying include or exclude. How might we score how well a model is performing? Before I get into that, there's just one brief thing I want to talk about, which is another machine learning term. It's called a confusion matrix, which is very appropriate for students often. But a confusion matrix is basically a 4x4 grid where you populate along one of the axes. In this case, along rows, we have the robots include or exclude, and along the columns, we have the human labels, or the labels include, exclude. And whenever on a given record, the robot and the human agree that both are included, we put that in the true include, or in this cell right here, we tally up 1 point. And whenever the robot and human agree on exclude, we also tally up 1 point here. And then, so basically the idea is every time you get one of these conditions, robot excludes, human includes, we tally up a count. So what Jeff was saying was, let's run through every record, and anywhere that the robot and human agree on include or agree on exclude, we're going to tally up points. And then our denominator is going to be every record, and our numerator is going to be the sum of these two diagonal cells here. And that's going to be what we would call accuracy, which I guess I'll jump right into. But takeaway from this slide is confusion matrix is an easy way to kind of build the counts of agreement that you need. True includes, false excludes, true excludes. Build these counts that you need to compute a lot of statistics that we're going to be using to analyze our model. So start with accuracy, just as Jeff pointed out. Accuracy is, stated in somewhat plain language, the rate at which the human and robot agree with one another, regardless of that being an include or an exclude. In this case, every cell in green here in the confusion matrix is used as a denominator for our performance measure. So let me just jump back for 1 second. If you recall, that's a poor choice of words. If you remember seeing these in the wild, these numbers always range from 0 to 1. The reality is that these 4 are actually just ratios. So these theoretically could be the same thing as percentages, or they are percentages. So always ranging 0 to 1, and you can see that in accuracy. That again, this is just a ratio. So I'm saying 88% here, but that is the same as 0.88. And that might be something that when we're thinking about making this more human readable or human friendly, we might think about making that a percentage instead of a decimal. So, okay, so accuracy, the rate at which human and robot agree with one another, include or exclude. You might look at this and say like boom, job done. We have a metric. This makes like tons of sense. Pretty much anybody that understands a screening model can understand that this is a reasonable way to measure model performance. However, I want to emphasize that we shouldn't only care about accuracy. It's not the be-all, end-all statistic. Consider, as a thought experiment, a model that only ever excludes records. It doesn't ever include records. That's pretty much a useless model, right? It doesn't add any information to a problem. If you were to consider that, like with this data, our accuracy would be 90%. And the reason that that's the case is 90% of the time records are excluded. So achieving a high accuracy doesn't actually tell us everything we need to know about how good a model is. Especially in our case, one extra thing to think about is like the utility of these different types of predictions. So to put this in kind of utilitarian terms, a false exclude, one of these guys down here, is a more expensive mistake than a false include. That's basically saying if the model tells a human that it's okay to exclude a record when it should have been included, that means a review is missing evidence. Missing evidence is a much more expensive problem, more problematic to the outputs of the review than it is to falsely include a record, which a human will just look at eventually and say, this shouldn't be included. Let's get it out of here. So there's kind of two angles to this. Number one, accuracy doesn't always measure real performance of a model, and it doesn't consider kind of the utility of a false exclude or a false include. Accuracy interpretation. If we were looking specifically at this model in a nest, we would say the way we might explain this to a user is the adjudicator and the model will agree, regardless of an include or exclude, 85% of the time from this number right down here. And one way we might interpret that in terms of time saving is that if you assume the adjudicator and reviewer are equivalent, the adjudicator will have to review about 15% of records in the nest. And that's kind of a gross assumption, but what it means is it's saving 85%. It's saving 85% of records that the adjudicator can just auto-adjudicate. Is kind of a very high-level way to think about this. And as mentioned earlier, you don't want to think in terms of accuracy in isolation, for the reason that a statistic like recall is actually more important to how we think about model performance. So recall is the rate at which the robot includes records that the adjudicator also includes, that humans would also include. So in our confusion matrix, there's only two cells that we care about. It's anything where the human said to include the record. So in our example down here, the robot and the human agreed on include 8 times, and the robot excluded something that a human said to include twice. So there's 10 total includes by humans, and the robot correctly recalled that those should be included 8 times. So our recall is 80%. This is the nature of recall. It's saying when a human includes something, the robot also includes it. What is the rate at which that happens? 80%. As mentioned earlier, recall is our most important statistic. Recall indicates that a review will be as comprehensive as possible. It will include as much evidence as possible. Having low recall would suggest to a researcher that their final review is going to be missing a higher amount of evidence, and that is a big problem for us. So recall is super essential. And I'm chuckling a little bit. I just pulled this example from a nest, so I wasn't cherry picking anything. This means if you truly had a recall of 100%, it means that every record your adjudicator would include, the model would also include. And so, like, if you were ever pitching this to someone, you'd be like, their mouth would be watering. They'd be like, "Wow, the model is, it's perfect. It never misses." And what that would mean is that if you truly had 100% recall, it means your model would be, or your review would be just as comprehensive as if you were using a human reviewer. In other words, the model is interchangeable with the human reviewer. Well, actually, I'm sorry, it is in fact better than a human reviewer. It has better recall than a human reviewer. No human would even have 100% recall. However, I just want to point out in this case that 100% recall is very likely not a real number, and it just signifies that the model kind of got lucky on this split of data. It just was able to learn very effectively this time around, and that we wouldn't actually expect it to generalize to 100%. We can say that we would expect it to generalize to a very, very high standard, though. Okay, and I'm going to move on to our last statistic here, which is precision. And precision is kind of, you can think of it as being complementary to recall. It's a way they kind of work against each other in the sense that you increase recall and you decrease precision. It's kind of one way to think about it. You can artificially toggle those two things up, and they trade off against one another. So precision is the rate at which the robot's inclusions are correct. So basically, we're going to look here, anywhere where the robot says to include the record, how frequently are those decisions correct? So if we look at our data, we have 18 total records that the model said to include, and out of those 18, 8 of them the human said to also include. So we have a ratio for our precision of 8 out of 18, which is 44% precision. That means that 44% of records that the robot said to include, the human also said to include. That might sound really confusing when you think about this in terms of recall, but it's kind of like if you imagine flipping the tables on the robot from recall. So recall is the rate at which the robot includes records the human would have included, and precision is the rate at which the robot the robot's inclusions are correct. So it's kind of like it's a little bit flipping those two things around, but it's important to think in terms of your denominators. And one thing I like to do is think in terms of our confusion matrix. Is, recall goes through these two cells and precision goes through these two cells. So one way we can describe precision is that precision indicates how much extra work the adjudicator will do. So if you have a precision of 44%, what that practically means is that you as an adjudicator, 1 out of 2 records that the robot includes that you're looking at, you will probably be marking as an exclude. So as you're jumping along, 1 in 2 records that the robot says to include, you will choose to actually exclude. And that amounts to extra work. The way we might describe this is that 85% of the time, the model includes a record. The adjudicator will also include that record. So you can imagine yourself in a nest, screening, going through adjudicating. This means that most of the time when the model includes a record, you're also going to ultimately say, yes, I'm going to include this record, regardless of excludes. If you see robot screener with a really high recall, like we see here, 100%, and we also have relatively high precision, 85%, it means that 1, the review is not going to be missing very much evidence, and 2, the adjudicator is not going to be spending a lot of time reviewing false include decisions. So really, like, this is an example of kind of a home run. Like, in this nest, we're really happy with model performance. We're saving a bunch of time, and the review is going to be just as comprehensive as if it were purely done by humans. So again, interpretation of precision. Anytime the model includes a record, the adjudicator also would have included that record. Briefly to touch on it, F1. So looking back here, F1 is another one of our magical mystery statistics. You can basically think about F1 as being the mean of precision and recall. And it's actually the harmonic mean, which is not intuitive to humans, in my opinion, at least. Just think about it like the arithmetic mean. Just think about like the mean of the two numbers. You'll notice that in this case, it falls kind of in the middle of precision and recall, 0.85 and 1. F1 is just kind of like the average of those two. Really, F1 is there for our more technical users. But if you ever see it, there's no real magic to it. It's just an average of those of precision and recall, which are pretty simple statistics to compute. How does this is probably the most relevant part to talking to users about interpreting model performance is, how do these numbers stack up against humans? Like, if we treated humans as if they were models, as if they were robot screener, what would their accuracy, precision, and recall be? So we actually worked this up for an ISPOR abstract. And in short, recall, which if we remember, is the rate at which the robot will include something that a human also would have recalled, or in the case of humans, is the rate at which a reviewer includes something that the adjudicator also would have included. Recall is 94%, and that compares with our robot at 97%. To be clear, this is across 20 different reviews, so the numbers are quite large. The number of records here are like 10,000, total included records. So quite high. So robot outperforms on recall by a little bit, which, as I mentioned earlier, is our most important metric. It's something we optimize towards. In terms of precision, human precision is typically 86%, and our robot achieves a 47% precision. So what you can kind of look at is say, okay, recall, it's equivalent to a little bit better from robot. And the way we're doing that is by trading off precision. Usually our model is going to have lower precision. And what that means is humans will be spending more time adjudicating false includes. In other words, records where the model said, I'm going to include this, and in reality, the adjudicator says, no, it's not relevant. What we're doing, like under the hood, is we are preferring to make a mistake to falsely include a record. The robot will always, if there's any doubt, will always prefer to include a record. And that means that our precision will be lower as a result. So a higher rate of false includes. Yeah, I guess the reason to just touch on why we're okay with that, number one, it protects how comprehensive the review is. And number two, false includes usually aren't that big of a deal in terms of time savings. If you recall, the average inclusion rate in a review is about 10%. So if we have a false include rate of, if we false include about 50% of the time, we have a precision of about 50%, it means that about 10% of our records will be false includes by the model, meaning that we really only increase the amount of adjudication work that somebody had to do by about 10% of the total records in the nest, versus previously having to adjudicate everything in the nest. So the penalty for false includes is actually not that high in terms of work put onto the adjudicator. This doesn't suggest you need to adjudicate 50% of the records. It actually means you need to adjudicate 10% of the records extra. So it's not as dire as the statistic might suggest naively. So in summary, when evaluating the model, when producing the statistics you see in the table, we use a technique called cross-validation, which is just using labels from already existing screening data. And then we evaluate 3 different statistics: accuracy, recall, and precision. What we would encourage users to evaluate these measures against is not trying to hit perfection, but rather matching human level performance in recall, which is, let's say, somewhere in the 90 to 95% range, and to think about precision in terms of how it's saving me time. So it's unlikely that you're going to hit human level precision, but higher precision at an acceptable recall is always better. So that's going to be one where it's a user judgment of how much time they're willing to save versus spending time giving the model data to learn from.